The sawtooth oscillator circuit shown here is implemented using 2 op-amps and 2 diodes and some number of resistors and cap. We want to show that the output voltage Vout is in the form of a sawtooth waveform as shown here. We want to see how this is possible and how the circuit operates, and also we want to find the period of this sawtooth waveform as a function of the components in the circuit. Okay, so the components we have are, aside from the 2 operational amplifiers and 2 diodes, 1 cap, 5 nanofarad in this case, 1 resistor R1, and also resistor R2 that is required to be practically much larger than R1, and also R3 and R4 as you can see. So we'll find that period as a function of these components. Let's make the assumption that op-amps are properly biased, so the, let's say, plus 5 volt supply voltage and negative 5 volt supply voltages are connected for both op-amps. So the consequence of that is for op-amp 2, this one, you can see that it is properly biased and in negative feedback. Output is connected via cap to input, negative input terminal. So it's in negative feedback configuration. And as a result, I can say for op-amp number 2. So for op-amp number 2, I can say for op-amp number 2, I can say, assuming it's biased since it's negative feedback, it's in linear region of operation, therefore virtual short is valid. And by virtual short, I mean the voltage at positive input terminal is equal to the voltage at negative input terminal for op-amp number 2. So positive terminal is grounded, so at 0 volt. As a result, negative terminal is also at virtual ground, 0 volt. Okay, for op-amp number 1, that's not the case. Output, V1 output voltage, you can see that output is connected via resistor R3 to positive input terminal. So it's a positive feedback configuration. Op-amp 1, as a result, operates like a comparator. So it just works as a comparator. As a result, what happens is, or sort of like a Schmidt trigger, so it just compared the 0 volt that is constant at the negative terminal with the voltage at its positive terminal, so V positive. So what happens is, for op-amp number 1, I'm going to write it here as a reference. So I'm going to write for op-amp number 1, I can say whenever V positive is greater than V negative, which is 0, then as a comparator, op-amp number 1 being an op-amp with very large open loop gain will immediately shoot the output voltage V1 at output of op-amp 1 to maximum positive saturation voltage, which is 5 volt. On the other hand, whenever V positive is, let's say, less than 0 volt, which is the voltage at negative, so at negative you can see it's always 0 volt. So 0 volt, then it, as a comparator, it would just immediately shoot the maximum negative saturation voltage at the output, negative 5 volts. So V1 becomes just negative 5 volt. Okay, so this is for op-amp 1 that is operating like a comparator. Alright, so to start, let's make the assumption that supplies are not yet connected, everything is at steady state 0, and suddenly we turn on all the supply voltages. What happens is, there will be always a noise. So output voltage at 0 suddenly, for example, experience just a little bit of a negative noise. So voltage at the output, and as a result, consequently at the positive input terminal that is connected via resistor R4 to the output, the moment Vout goes a little bit down, or positive terminal of the op-amp 1 goes a little bit down from 0, what happens is we will be dealing with this situation. And as a result, V1 goes to negative 5 volt immediately. So Vout remains at 0 roughly because we are tied to the cap C, which on one side of it is connected to virtual ground. So one side of this cap is 0 volt. And let's say the polarity of the voltage of cap is like this. It's something we can define. Okay, so voltage of cap as a function of time at the beginning of time 0 is 0 volt. And that's tying the output to 0 at this starting point. But then, since V1 is at negative 5 volt at this in this moment of an analysis, it will immediately shut down diode D1 and it would turn on diode D2. So from perspective of op-amp 2, at time 0, so let's say we are exactly here at time, let me make sure we are at the center, so we are exactly here at time 0, and output voltage Vout is 0 at the beginning of the operation of circuit. And what happens is, because diode D2 turns on, what happens in the circuit, it tries to, the 100K or R2 will notice a 0 volt on one side and negative 5 volt on the other side. So as a result, what happens is, there is the current of I, let's say I1, or let's say I2, because we're talking about diode number 2, I2, that is passing through this 100K, and nothing can go through the negative terminal of ideal op-amp because it has infinite impedance, especially for this op-amp that is in linear region of operation. So that should come through the cap like this. So all I'm saying is, from perspective of op-amp number 2, the situation we are dealing is this situation. We have effectively V1. So let me make sure that we have the right color here. So there you go. We have V1 at the output of op-amp 1 connected to 100K R2, and then this goes to negative input terminal of op-amp 2, and then from there, via a cap of 5 nanofarad, it goes to the output Vout. In this circuit, that, as I just explained, there is this current I2 that is flowing, and let's not forget V1 at this moment is negative 5. So if I, just for the sake of reference, if I just continue the plot, so let's say if I also show V1 while I am showing Vout here on the y-axis on top as a function of time, let's say I also have V1 shown here. So there you go, V1 at the output of op-amp 1. At time 0, V1 is negative 5 volt. Okay, and as time is increasing, we are at negative 5. And as a result, negative 5 resulting in 0, negative 5 across this 100K, this current I2 flowing, and I2 is simply 0 minus minus 5, so 0 minus minus 5 divided by R2, or basically 5, in this example, divided by 100 kilo ohm, and as a result is 50 microamp. So that's the value of I2. This I2 is going through the cap, as you can see here, and given that we assume that the polarity of the voltage of the cap is like this, and because on one side cap is tied to ground, because the negative terminals of our op-amp is at virtual ground, then as a result we see that voltage of cap at time t minus the initial voltage of cap, which is assumed to be 0, so minus 0 initial voltage, is equal to 1 over c. When the current is going through the cap, it is charging up the cap with the polarity I'm showing, and therefore it's just integration of the current that is going through the cap, which is, as we talked about, I2 here, dt. So we get voltage of the cap, or basically Vout, because Vout is equal to Vc, or voltage of cap, is simply 1 of I2 over C T. So we can see that the output voltage during this, right after start of time equal to T0, is linearly proportional to time. So there you go. We are increasing, I'm showing on top, so I'm showing that the voltage Vout is increasing as time is increasing. And the question is up to what point? So what is this Vmax at the output? So what is this Vmax or Vm at the output? Okay, so take a look at what we have here. So I'm going to focus on what we have on the schematic of the circuit. So we have V1 5 volt at the output of op-amp 1. We have V out that is increasing, negative 5 volt for V1. So in this circuit, as a practical example, we make the assumption that R3 is equal to R4 equal to R2, all of them 100K. So what happens is, as the V out is increasing from 0 volt onward, the moment it gets close to 5 volt, which is the maximum saturation, positive saturation voltage, because R3 is 100K and R4 is 100K, and because on one side here we have V1 5 connected to R3, and on the other side we have R4 connected to V out, which is increasing toward 5 volt finally. When V out gets to 5 volt, as it is increasing, the midpoint here between R3 and R4 will get to 0 finally. And the moment, because of the symmetricity that we have here, R3 being equal to R4, and because we already have negative 5 volt on one side of R3, the moment V out reaches 5 and tries to go even a little bit beyond 5 volt, then this midpoint voltage at connecting to positive terminal of op-amp 1 will try to become going a little bit above 0, which is good enough to result this comparator change its decision and switch the output immediately, V1, from negative 5 to 5. So negative 5 to 5 immediately. So this Vmax is 5 volt. The moment we get to that, what happens is, I'm going to show a different color. So let's switch to green so that it's observable. Okay, so V1 at this point jumped to just plus 5 volt. Let me show it here. So plus 5 volt. Okay, so V1 is 5 volt. So immediately when that happened, diode D2 turns off and diode D1 turns on actually. So, and as a result now, the whole story changes. The current I1 start flowing through the cap with this direction. From left to right, which is counter the current of cap. It will try to now discharge the cap, but now we have initial condition, so the circuit looks like this now. So I would say the moment that diode D1 turns on, circuit looks like this. Circuit becomes, alright, so we have V1 equal to 5 volt connected to resistor R1 now of 1 kilo ohm as is shown, and then we have connection to negative terminal of op-amp 1, op-amp 2, and then we have the cap C 5 nanofarad, and again the definition of voltage of cap is like this, and this time we have initial condition because V out got to 5 volt already, and on the other side we have virtual ground, so this cap has 5 volt on one side, 0 volt on the other side, so there is initial condition. The current that is now passing through the cap like this has to work out the initial condition and change the polarity. So there is an interesting phenomena going on. This whole thing happens way faster than before because now the value of resistor 1K is much smaller than the R200K by a factor of 100. So whatever happened before that I described here and I described here is going to happen 100 times faster. So let's just write down the equation one more time. Equation is like this. Voltage of cap at time t minus initial condition, so V cap initially, is equal to, okay, same as we saw here, but now is going to be I1 over C times T. And T is the, let's say, the duration of from starting time of this procedure at time T1 here. I'm going to highlight on the diagram. So if you take a look at top diagram, the moment this whole thing starts, I'm talking about, so initially we were time 0, now we get to time 1, and then whatever it takes to get to time T2. So from T1 to T2. So initial value of cap with the polarity that we have defined here, of course, is just equal to 5 volt. So that's 5 volt. But what is the condition we are chasing? So as this current with the direction that I am showing is flowing through the cap, it starts reducing this 5 volt at the output to lower values. Down to where? So that's the question. Down to what value? Down to what? So the answer to that is, take a look at the circuit. So now we have, for the same thing we talked about, this time, output voltage has to get down while the V1 connected to R3 is at 5 volt. So again, due to symmetry that we have R3 and R4 equal to each other, midpoint need to get below 0 so that voltage at positive become less than negative for the Schmidt trigger or comparator to reverse the decision. So that requires V out to get to negative 5 volt again. So negative 5 volt. As soon as V out get to negative 5, this midpoint get to 0 and try to go lower. And that's the moment that op-amp notices that, op-amp 1 notices that the voltage at negative is higher than voltage at positive, and then will switch the decision back to negative 5. So all I'm trying to say is we need the V out to go down to get to negative 5 volt. We need the V out to go down to get to negative 5 volt. That's what we need to happen. So the final voltage that we are targeting is negative 5. And remember, VC is equal to V out, just because of the polarity of VC, voltage of cap, because on one side cap is tied, as I said, on one side cap is tied to 0, and on the other side cap is tied to output V out. So VC is always equal to V out. Okay, so let me go back to my color, so to black here. So what I have as a result is minus 5 equal to current I1. We have to put a negative sign there because that is current of cap is this direction according to the polarities we defined for the cap. So IC. Now I1 is counter that direction, so minus, and I1 is now just simply 100 times what I2 was, because we are dealing with 5 minus 0 divided by 5 minus 0 on two sides of R1 divided by the value of R1, which is 5 over 1K, which is obviously 5 milliamp, which is 100 times more than the I2. So, as expected. So as a result, we get minus, in this case, we get to minus 5 milliamp divided by the value of cap times T, or T2 minus T1, the duration that this thing happened. So given that C is 5 nanofarad, this whole thing indicates that duration, so this T2 minus T1 is duration of V out reduction. So duration of V out reduction. So we can, from this point, we understand that the T2 minus T1 is equal to, as a result of this whole thing, is roughly equal to, you can see, is about, just to make sure I'm not missing something, we have 5 milliamp over 5 nanofarad on one side. That translates to 10 to the power, let's say, just to make sure I'm not missing something. So on the other side, we have 10 here, negative cancel out, and then we have 5 nano and 5 milli, which means we are talking about this is nanofarad, so nano versus milli, that will result in 10 to the negative 6. So you're talking about 10 microsecond. For duration of downtime. All I'm trying to show here, and of course this means that duration of uptime, which depends on current I2 and resistor R2 that is 100 times larger than resistor R1, is going to be 100 times slower. So the output voltage, if we zoom in, the top diagram here, if we zoom in to the output voltage, it looks like this. So I am showing it here, making sure I'm not. So it looks like this. Okay. V out. So we started tracing at, say, time 0. And then let me just make sure. Okay, there you go. And I need to sort of try to visualize it, which is not easy because of scale of 1 to 100. It's not exactly showing what is happening, but there is no other way for me to show the scale of 1 to 100. So duration of increase, this is time t equal to 0. This is the value of plus 5 volt. This is the value of negative 5 volt for V out. And what is happening is duration of downtime for V out, this duration, we discovered that to be 10 microsecond. So this duration is 10 microsecond. And duration of increase for V out in this practical sawtooth generator is now 100 times that, because the resistor R2 is 100 times of R1, and hence it takes 100 times to do the same thing that we did with R1. So this is 100 times 10 microsecond, which is 1 millisecond. So effectively, this 10 microsecond is negligible compared to 10 millisecond. I mean, the scale is not showing it exactly because this is 100 times longer, 100x. So all I'm saying is effectively the overall period for this practical sawtooth is the value of T1 plus 100 times, which is plus T2, which is 100 times T1. That becomes the overall period of this practical sawtooth. So the overall period is equal to sum of T1 plus T2. Now if we sum them up, of course, we can say T, or the period of this thing, is T1 plus T2, which is effectively, as we computed, is just end up to be 1 over, it becomes just 2 times the value of the resistor together. So R2 plus R1 times C of the cap. So in this case, we can approximately say it's just 2 times R2, or I put it here, because R2 is much, much larger than R1. Therefore, we can basically neglect R1 and say T is just 2 times R2C. And if you plug in, just as an example, again confirming what we found, C is 5 nanofarad and R2 is 100K. So, and then times 2. So 2 times 100K times 5 nanofarad, it become exactly what we wanted. It become 1 millisecond. So effectively in this circuit, with the example choice of the value of components, we realized a 1 millisecond period roughly sawtooth waveform, or about 1 kilohertz sawtooth waveform frequency. So by adjusting the value of components, we can also play and increase or decrease the frequency of this sawtooth waveform. I hope that this example is helpful to show how in practice we can have a practical circuit with minimal number of components and op-amps and diode to implement a sawtooth oscillator or sawtooth waveform generator that is shown here.